Hello everyone, welcome to Cybernetic Systems Design and Dynamics. This is Learning Activity 3 where we're going to go into control theory and system modeling. This will be a shorter lecture because I don't want to take too much of your time this week on longer lectures. I've got a lab that we have to run through. So I'll spend a little bit of time on a little bit more info on control theory and then a little bit on system modeling, and then we'll jump over to the lab this week. Okay. So to start off, let's jump into a little bit more control theory. We talked about control and stability in our last learning activity. This week I'll be diving into a little bit more and just kind of to add a little bit more meat onto the conversation here is that when we're talking about control theory, we also need to be cognizant of two concepts that we didn't cover last time, which is linear control as well as nonlinear control. And when you look at linear control systems, they're super simple. They're not really, they're good for educational purposes, and they're also good for very simple machines. And the application of control theory as it relates to simple machines is where you see a lot of that happening, like thermostats, cruise control in a car, and other simple gadgets like that. You know, just some real simple input and a simple output, things that we're controlling for. Like, for example, in a thermostat, all we're controlling for is temperature input, and we're controlling temperature output. So control theory, I mean, I say that it doesn't have a lot of wide applicability, but that's more kind of on a broad scale for more complex. So when you scale control theory up, linear control theory kind of goes away. On the other side, nonlinear control theory, as you scale up, that's you kind of find yourself more in the nonlinear space or the polynomial control theory space. And what ends up happening on the nonlinear side is it's broader, it's more applicable. Of course, it's more complex, right? To model out nonlinear systems is unbelievably complex, and actually, it doesn't take long. And as you'll see in this week's lab, it does not take long for us to get into a control system, even a really basic one. The more you start to try to control for different variables within control theory, the more you're like, wow, I really don't understand what's going on within the system. And there's a lot of interesting aspects to control theory that also apply in artificial intelligence, especially as it relates to decision trees and neural networks. So that's kind of something to be kind of on the lookout for. But for our purposes in design and dynamics, one of the things that we're not really, we don't want to go too far into the weeds, because I'm trying to make sure that you maintain a healthy understanding of the macro level, right? The system level. But one of the things that we do want to talk about when it comes to control theory is that it's largely based on superposition, so superposition principle. And that's essentially saying that for any given linear system, there's a net response caused by two or more stimuli, and that is the sum of the responses that would have been caused by each stimulus by themselves. And so if you kind of write it out symbolically, for every input A that's it produces a response X, and input B produces a response Y, then the input A plus B will equal the responses X plus Y. That's kind of a, so the top is the more detailed formulation, whereas the symbolic representation is a little bit easier to digest. If you're interested in the math behind it, I took a snippet here from a website that I like, and then you can kind of take a look at that and dive into the details of the math if you're interested. We are not a math class here, so but we're not going to be doing we're not going to be working out superposition problems as it relates to control theory mathematically. We will be working out control theory problems through models. So that is something we're going to be doing in labs from a loopy perspective. All right, so really, I think it comes down to application for us, right? So if this is all, fine, but why do we even need to be aware of superposition as it relates to control theory? So it has a lot of applicability, and also you can impress your friends that you learned about superposition in your class. But when it comes to superposition and its application, it shows up in a lot of places in electrical engineering. I'm not going to read through all of it. I'm just going to let you you can pause me and read through this piece of it. But from electrical engineering to physics to process control, all the way to music and computing, superposition has a place in a lot of different aspects of science and technology. Okay, so this week for it's easier in my opinion. It's so much easier to talk about control systems, control theory rather, through modeling real world examples. So we're gonna do two. I'm gonna pick two. I'm gonna pick a single input, single output. We talked about this a little bit in our last lecture. I'm also going to talk about multi-input, multi-output. So just as a quick recap, when we talk about single input, single output, systems are less complicated. They're easier to make, and like I had said earlier, they're kind of good for single purpose filled situations like a thermostat or cruise control on your car. MIMO systems, multi-input, multi-output systems, usually are very difficult to manage and model. And so you'll see in our lab this week that just on one of the examples that we're going to go through, it's going to be pretty interesting how complicated it gets with something that we think is so simple. So as it relates to MIMO, multi-input, multi-output, we have systems. They're more broadly applicable, like just kind of to recap before we talk about the two systems or two models that we're going to build out in Loopy. But there's usually, of course, you've got more than one input, you got more than one output, and they are a lot more complicated than CISO systems. So for us, what are we going to be doing? Well, to put a bow tie on this very short lecture that we have this week, we are going to be using Loopy. So I'm going to step you through how to get logged into that and get going with your system dynamic model. We're going to actually create a systems dynamics model using Loopy. We're going to model out two. We're going to do cruise control, which is going to be a single input, single output, because it's managing speed. That's it. So we got speed for an input and we got speed for an output. So on the MIMO side, for the second part of our lab this week, we're going to do growth of a plant. So we're going to do multi-input, multi-output, and that'll just about wrap us up for the lab component this week. So if you have any questions, as usual, feel free to reach out. Don't hesitate to send me an email or text. The other thing I'll say is also, because of the way this course is set up, make sure you get your discussion boards in. Make sure you get that taken care of and your teams finalized this week. Just a quick public service announcement to make sure you've got that kind of hammered out. If you have questions on that, again, I'm here to help. And with that, I will see you in the next learning activity.